let me walk you guys through this lab. And there was some modifications that were done, and maybe you might still have the old version. The old version dealt with lentil and soybeans. We found out that those things are not very stable. They pick up moisture, the mass change. And so we had to change that experiment. And so I figured, hey, why don't we just do Legos? Legos, in my lecture, generally, I say that atoms are the building block of matters. They are like Lego pieces. You take the Lego bricks and you put them together and you can make whole cities like Legoland. And that's basically how atoms operate. Of course, at a more sophisticated level, but still it's the same concepts where they are the building block of whatever we see around us, just like in Legoland. So what I want to do today is I just want to walk you through the lab. If you click on this first part right here, what you will see is the information for this lab, okay? And the PowerPoint's here, as well as the lab manual. The lab manual has actually been updated. So let's take a look at that. So this is the portion of the lab that was updated. Still have the same beginning portion where you guys will need some nuts and bolts, but instead of lentil beans in this particular section, you see some Lego pieces. That's what's changed. Then the unknowns are approached the same way, except for this last part, this part right here, where it says the number of molecules, EF2. EF2 stands for the Lego bricks I label E, and the Lego bricks I label F. It has to do with the number of pigs. So if you have a Lego, and you guys all have Legos in your kit, let me just show you that real quick. So these are the hardware that you guys will need. These are the Lego bricks, and you guys should have a packet that has 2 of these, and right here, okay, 2 of these and 2 of these right here. So you have something that looks like this in your packet. Okay, something that looks like this. Oops. There you go. And it will be different colors, but the colors are not going to make much difference because the color doesn't change the mass. So that's the brick. And I call these bricks either an E brick or an F brick. And it has to do with the number of pegs. Let's take a look at this. If you take a look at this, you have 1, 2, 3, 4, 5, 6, 7, 8 pegs. So it got 8 pegs. I labeled this the E brick. If you take a look at this, I've got 4 pegs. I call this the F brick. So an EF2 would look like this: 1E, 2F. So that's the bricks. Okay. So hopefully you guys can saw that. Let me get out of here. Let me walk you through this experiment. Okay, this is the lab manual. You guys are going to be weighing these guys, so you have a baseline mass, just like we have the mass of the chlorine atoms, the carbon atoms, and the aluminum atoms. Okay, well, these are going to be your building blocks for our little experiment. You've got the hex nuts, you got the bolts. So in terms of the hex nuts, you guys are going to be given, you guys should have a packet that looks like this. Okay, and this packet will contain bolts and hex nuts, bolts and hex nuts. And what you need to do is you need to take your, this is called a B, it's called a BN, it's called a BN4. Why is it a BN4? Because it's got 1 bolt and 4 nuts. So unscrew all of these and get all your nuts together. Okay, hardware nuts here. And then make sure that when you turn on your scale, you put a weighing bolt there to protect it. Make sure that when you place your weighing bolt, that you tear it so it's 0, and then put your hex nuts right in there and put all your hex nuts on there. So you get the total mass of all the hex nuts. So that's the first thing that you want to do, is you need to disassemble these things and put your hex nuts right there, and then get the total mass. And in this particular case, I have, let me just count real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 here. You guys should have 10. But my mass reads 33.53. So the whole 11 nuts are 33.53. What I need to do is I need to get an average. So what I would do is I would take that mass and divide by 11, and that would be the average mass of one hex nut. So that's how you get the mass of one hex nut, because we need an average, because these things are going to vary from one hex nut to another. For example, if I just take one of these, make sure that this thing is tare. Okay, it's tare. And I put this hex nut, it reads 3.03. But if I take another one and I put it on here, it reads 3.02. So they're not exactly the same, but what I can do is I can take an average. And you know, that's not so different from the elements in the periodic table. When we grab a handful of carbon, we're not grabbing carbon 12. We have carbon 12, carbon 13, carbon 14 in that handful. And what we do is we get the weighted average. So that's what we have when we put all these hex nuts here. We take the total mass that our scale is giving us. Okay, that our scale is giving us. And then what we do is we divide it by the total number of hex nuts that we have, in this case 11, and then that would be the average. So that's how you would get this value right here, the average mass of one hex nut. Now, what you need to do next is do the same thing for the bolt. You guys should have about 4 bolts, but whether you have 3 or 4, doesn't matter. Make sure again that when you start, you always tare, that's T-A-R-E, your scale. Sit right here. Make sure you tare your scale so it's 0. And then you put your 4 bolts. You read the total mass and then you divide it by 4. So you always divide it by the number of items that you have that you're weighing. That'll give you the average. Okay, so that's this right here. Then what you need to do next is, if I have 4 bolts, then I can make, based on the hardware that I have, this is a BN1. Why? Because it's 1 bolt and 1 nut. That's 1. That's 2. Now I'm just randomly taking any hex nut that is available. I'm not specific. That's 3. That's 4. So what I'm going to do is I'm going to weigh the 4 BN2, take the total mass, and then divide it by 4. That will be the average for 1 BN molecule, and that's what you would put right here. Okay, for BN2, I can take a shortcut. I can do this. I can either take one of these and put another bolt, or I can just add, not even weighing, not even tying it in, 3 more on here, and then I'll take the mass and divide by 4 BN2. Okay, and that's what I would put right in my data sheet right here. Right here, I would put it right here. Take the total mass, divide by 4, and that would be the average. For BN3, what I could do is I just add 4 of these hex nuts. Okay, now if you're running out, then what you need to do is you remove one of these BN2s. You don't have enough hardware, but because what you need is a whole BN3, a whole BN3. So right now I've got if you look right there, I've got 1, 2, 3 BN2s, but I don't have enough hardware for a BN3. So what I'll just do is weigh 3. 1, 2, 3. That would be a BN3. I would read that mass and divide by 3 instead of 4 because I don't have enough for 4. And then a BN4, that's even trickier. I can only do 2. Okay, so this is a BN3 right here. This is a BN4 right here. And because I don't have enough hex nuts, I can't do 4. I can't even do 3. I can do 2. Depending on how, the more you have, the more accurate you will be. And why do you want accuracy? Because your grade will depend on it. You guys have to be able to count the right amount. So that would be 2. I would just take that mass and divide by 2. Okay, and then I will put it right here. I put it right there. So once you have this, you're going to be using that information when you actually do the counting by weighing. This is your E brick, and this is your F brick. Okay, so what do? I think you guys have this setup right here. You guys have this setup right here. Something like that. Okay, 2 F and 2 E. So what you need to do is you need to break them apart and just weigh your 2. Again, tear your scale. Weigh your 2 E bricks, record the mass, and divide it by 2. That's what you put in C1A. And then you take your 2 F bricks, take the mass, and divide it by 2. That would be down here, C2A. Okay, and then this part right here, the video, let me show you the video. So the first part just explains how you would weigh these things, okay? But if you scrub through and you go to the second part, you'll see the bricks. So what I've done here, and I apologize for the poor quality, okay? But you can still read the mass. For this one F brick, it's 1.14 grams. For this other brick, this is Lego piece number 5, that's 2.2 grams. What you can do is, what I did was I weighed them individually, but over here, you'll see that I took all of them together and weighed them all out, 10 of these, and it looks like it weighs 11.50. So in order to get the average mass, you don't have to go through the individual ones, but the average mass, we just take 11.5 and divide it by 10. Now I do the same thing for the E bricks, okay? Do the same thing for the E bricks, and you can just scrub through, and here it is. For all 10 E bricks, what you have is 22.73 grams. What you need to do is you need to take that and divide it by 2. Then I do the same thing for the EF2 bricks. Okay, I weigh them individually. And then I put all 10 on a weighing boat. And then what you can do is take that total mass and divide by 10. And that's basically it. Once you weigh the hardware, the bolts and nuts and the bricks, then you're done with the measurement portion of this particular lab. Well, not really. You still have to weigh out the sugar, and you need to weigh out 50 milliliters of water. Okay, so I'll show you that. But that's the video. That's the video that you will see. That's this portion. So the first part is your measurement. The second part is from the video. First part is your measurement. Second part is from the video. This is EF2. So the EF2, your measurement, okay, and then from the video. And then what I would like to do is I would like to figure out what exactly is the percent error between your measurement, which only measures one EF2 molecule. So you take your measurement that you weighed out, and that would be this right here, E3A, and you take the average from the 10, and here, and you count a percent error. The percent error is going to be your measurement minus the video divided by the video times 100. So that's not really a percent error, percent difference. Okay, so that's that part. And then the other thing that you guys need to weigh out is you guys will need to weigh out, take your graduated cylinder, take your scale, turn on your scale, and then place your graduated cylinder on your scale. It should read a mass. Okay, it should read a mass. What you can do is that you can tear it, of course, or you can just start from 0, place your graduated cylinder there, record the mass. What you want to do next is fill your graduated cylinder with water, 50 milliliters of water. So what you want to do is you want to fill this with 50 milliliters of water, and then put it back, and then weigh it. You need the mass of the 50 mils of water, and the 50 mils of water should weigh approximately 50 grams, plus or minus. It doesn't have to be exactly 50 mil, but try and get as close to 50 milliliters as possible. Remember the precision of these things, write it to the correct precision of the graduated cylinder. Okay, so that's this portion of your lab, the 50 milliliters of water. And then you guys are going to be asked to weigh some sugar packets. So in the sugar packet, what you will have is this right here. So what you could do is, sugar is pretty safe. Okay, this definitely is sugar. Let me show you. Okay, put the sugar packet there, and then dump out the sugar. Dump out the sugar, and then weigh the packet empty. The difference between the packet and the sugar and the packet is the mass of the sugar. Okay, and make sure you use the precision of the scale. So again, you take your sugar, you weigh it, make sure it's 0 in the beginning. Okay, make sure it's 0 at the beginning. You weigh it as a whole, then you empty it out and you weigh the empty container. That difference is the amount of sugar that you had in that packet. And that's what you would put right here. Okay. And after that, then you're pretty much done with the measurement. So at this point, you have the mass of one hex nut, the average mass. You have the mass of a bolt, the average mass. Okay. You have the mass of an E-brick, your measurement, and then the average from the video. You have a mass of an F-brick, your mass, and the one from the video. And you have a mass of the EF2, your mass, and the one of the video, and then the percent difference. How accurate, in other words, is your measurement relative to the one in the video? Don't try and fudge it, okay? Don't try and make yours closer to the one in the video. Just write that out. There's no right and wrong. It's important because then it will tell you your percent error when you actually do the calculation. Then you need to go to Canvas. Let me show you this real quick. And you need to go to this section of Canvas. You go to Module, and then go to this portion of Canvas. Access, click here to access your unknown. Each of you will be randomly given an unknown, okay? So when you click here, I'll do a preview. This is unknown number 4. There's going to be 10 unknowns, okay? And do a screenshot of this. You have a mass of the container that's 14.66. You have a mass of the container plus the Hex Nuts 98.8. So if you subtract the mass of the container, you now have the mass of the Hex Nut in that bulk, and that bulk looks like this right here. Okay, that bulk looks like that. You got the container, You got hex nuts in that container right here. And what you need to do is you need to figure out how many hex nuts in there. It's counting by weighing. So that's the data for the hex nuts. If you take that net mass of the hex nuts and you divide by the mass of one hex nut, which you have right here, then you can count how many hex nuts are in that container. So that's how we count by weighing. We use the data that we have. We use this information. Remember, you have to subtract the mass of the container. And if we divide the mass by the mass of one individual piece, then we have the total number of hex nuts in that particular container. You do the same thing for BN1. You do the same thing for BN1. For BN1, what you need to do is you go over here. This is a BN1. The mass of the container plus the sample, the mass of just the sample. And if you divide that mass by the mass of one BN1 right here, then you'll be able to tell me how many BN1 molecules are in that container. You guys don't have the container, but if you were in Miramar, you guys would be given a bucket and you would have to do this manually, experimentally to do that. We don't have enough hardware, so you guys would just have to use this database to do the calculation. Then we have EF2. Okay, we have EF2. EF2, again, go to your unknown. This is the mass of the container. This is the mass of EF2 and the container. You have to subtract that off. And then you divide by the mass, go over here, of, use the more reliable data. Use the more reliable data. Get the average mass of one EF2. If you get the average mass, that'll be a better indicator rather than your particular mass. C3A, use C4A. And when you do that, then you can tell me how many EF2 molecules are in this container right here. Pretty easy, okay? It's not that difficult. The idea here is, again, counting by weighing. And in chemistry, real life, that's what we do. If we have a handful of oxygen molecules or water molecules, okay, and we know the mass, and we know that for the water molecules, 18 grams per mole, if we take the mass of that water and divide by 18, then we know how many moles of water molecules is in that container. We just need to convert that moles to molecules using Avogadro's number. And now we've been able to count the number of molecules within experimental error in that water container. Counting by weighing, that's what we do because the individual pieces are so small. That's what this lab is about, counting by weighing. Now this right here is a little bit different. It's not that tricky, but it's a little bit different. Your unknown will tell you the number of molecules. So let's take a look at your unknown. Again, don't submit this until you fill this out. Once you fill this out, then you can submit it. For molecular G, there should be information here in terms of the number of molecules. I think that's what's missing here. I need to tell you the number of molecules each one of these contain. I don't know why it doesn't say that, but it needs to tell you the number of molecules here. Okay, so I will put that in these right here. Otherwise, you can't answer these questions. But let's say that there are 8. There are 8. So you put 8 here, and let's say that this has 4. You'd put 4 here. The next thing that you would do is you would need the mass of the container, the mass of the container plus the chemical, the mass of the container, so you have your gross mass. Okay, what you can do next is you can take this gross mass of just the hardware and divide it by the number of molecules. So that's what's missing here. Once you have this right here and the mass of the hardware right here, you divide it. You take that mass and divide it by the number of molecules. Okay, so if you got 100 and each molecule weighs 10, 100 divided by 10 is 10. that would be the mass of one individual chemical. So what you want to do next is you want to go to your database, this right here, and you compare it to BN, BN2, BN3, or BN4. Which individual mass is closest to the individual mass in G? Okay, because when you take this mass and divide it by the number of molecules, you will have the mass of one molecule. Okay, a BN, BN2, BN3, or BN4, depending on what you have. So you need to take G4 and divide by G1, and that's the average mass right here. And then you go back to your data right here and figure out which one's the closest. Whichever is the closest is the formula that you have for your unknown, whichever is the closest. So we're not asking you to calculate it from no man's land. We're asking you to compare to your data. So that's what this is right here. Then you do the same thing for H1. Again, what you will do is you will figure out the mass of the hardware in here, which you can't see, but you will know how many there are. Like in this one right here, it shows you 8, and here it shows you 6, but that's not true because your different unknowns will have different amount. So that needs to be included right here in the unknown. It has to tell you what that is. Otherwise, you can't do the calculation. But once you do that, then you can give me a formula. And that's basically it. That's the hardware portion. The next part of this is weigh your 50 milliliters of water, weigh your sugar. Okay, and that's your data. In the calculation, this is your PreLab. You guys want to put that data in here again, and then calculate your moles of water. And remember that your moles of water, you guys know how to do that. Let's say that my water is 49.37 grams. Remember that your scale is able to read mass to the closest. You know that water is 18.01 grams per mole. You can figure out the moles of water. If you want to know the molecules of water, then you would take the moles of water. Let me just get a number for this real quick so that we have numbers to play around with. If I do this, 49.37 and divide by 18.01, I get 2.74, and I'm using 4 significant figures, 1 moles of water. If I put 2.741 moles of water, and I use Avogadro's number, that's 6.02 times 10 to the 23rd molecules water in 1 mole. Then I now have my molecules of water. So that number comes out to 1.650 times 10 to the 24. It's stuff that you guys learn in Chemistry 200. Now, suppose it asked me for the number of hydrogen atoms. Well, you know that for 1 molecule of water, you have 2 hydrogen atoms. That comes from the formula. So you can do this, 1.650 times 10 to the 24 molecules. You can say that for every 1 molecule, my abbreviation for molecules, MOLC, water, you got 2 hydrogen atoms. And if I do that, then it's just taking my answer, multiplying it by 2. And that's how many 3.300 times 10 to the 24 hydrogen atoms that I originally have in this 49.37 grams of water that I weighed out. Okay, so that's the calculation that you guys do in this. It's basically chapter 7 right here. That's number of oxygen atoms, number of hydrogen atoms. You do the same thing for sucrose. Sucrose is a little bit more complicated. Reason why it's more complicated is because it's got a formula of C12H22O11. So whatever mass you weigh out which is what you would put right here. Okay. And then look up the mass of sucrose or calculate it. 12 times 12.01, 22 times 1.01, 11 times 16. That would be the molar mass. Why do you need that? Because again, in order to convert grams of sucrose to moles of sucrose, you need the molar mass. So you need to put that right here. Okay, calculate the number of moles of sucrose. Now that you now have the mass, let's say that we got 1.87 grams. And sucrose is about 180 grams per mole. You can use that 180. Make sure you have a more precise value for that molar mass. Grams per mole. Now you have your moles of sucrose, which is table sugar, by the way.
Professor,
Mm-hmm.
I have a question. So how do I figure out what J6 would be, the sucrose sugar?
J6 right here is just the mass that you weighed out. It would be this right here. Remember I showed you that you take your sugar packet. You guys all have a sugar packet. You weigh it.
Okay.
Okay. And then you empty it out and you weigh the container empty. And that difference is the mass of the sugar. Does that make sense?
Got it.
Okay.
Thank you.
So that's how you would do that. And you guys all have approximately the same amount. So you should all get approximately the same amount of moles. So that's what we have right here in terms of that. The molar mass is here. The moles, like I said, you just do this calculation right here. You say, let's say we have 1.87. We use the molar mass to calculate the moles. Now that we have the moles, we can use Avogadro's number. 1 mole equals 6.02 times 10 to the 23rd molecules. And then we have our molecules of sucrose. Now, this next part right here, it's a little bit tricky, but it's pretty straightforward. For every 1 molecule of sucrose, yeah, that is your conversion factor. So if you know the molecules of sucrose, okay, and you want to know the number of carbon atoms, then you do this. For every 1 molecule sucrose, you have 22 carbon atoms. And when you do that math, you will calculate the number of carbon atoms right there. It's your conversion factor. This right here is your conversion factor that will take you from molecules of sucrose to carbon to hydrogen to oxygen. So you just change the conversion factor if you want carbon, hydrogen, or oxygen in here. And that's how you would solve these right here. Okay. You take the molecules of sucrose and you either multiply by 12, 22, or 11, and that'll get you the carbon atoms. And then you're pretty much done. That's your lab. Okay.